Hello dear students, welcome back. We are now in part 5 of Gravitation Chapter. So let's quickly revise what we did in the previous lecture. We talked about the fuel requirement for satellites, and we understood that for a satellite to go in an orbit around Earth, right, it doesn't require any fuel except for the launching requirements. Alright. Then we also saw the concept of centripetal force. It is because of this centripetal force, which is given by the gravitational force, right, the satellite is actually able to go around Earth without any fuel, right? Then we also talked about the concept of space debris, because if satellites just keep on revolving around Earth and after their lifespan is over, right, they continue to revolve, and that is going to cause a lot of what we call as kachra, right, space debris in space. So then we talked about the time period of satellites, and we understood the formula T square proportional to R cube. Okay. So let's begin today's class. So today, first thing we are going to talk about is Kepler's law. Okay, so Kepler gave 3 very important laws based on which a lot of numericals we are going to have a lot of MCQs. Okay, so the first law, let's begin with the first law. First law is also called as the law of orbits. Okay, so what is this law? So he's talking about the planets. Okay, every planet in our solar system, okay, it revolves around the sun in what is known as an elliptical orbit. So we already saw this shape, right, for the different possibilities for the trajectory of the satellite, elliptical shape, right? So all the planets go around the sun in an elliptical orbit. Now every ellipse has what is called as a focus. Okay, so the sun is at one of the focus. So what does this mean? So you can see this blue path here is the elliptical path, right? This is our planet. Now every ellipse has something called as 2 foci, like the plural of focus is foci. So this is one of the focus, sun, and at the other focus we don't have anything. Okay, I mean the sun can be here, it can be here also. It depends on your point of view, right? It depends on the orientation of the diagram. So sun is one of the focus, and this planet is going around the sun in an elliptical orbit. Okay. This is Kepler's first law, right? Then Kepler's second law. Now this second law is actually more interesting. So before we understand the second law, let's understand something about brooming or sweeping. Okay. So you can see this person here, he has a broom, jhadu, right, in his hand. And what is he doing? So you can see he's sweeping, right? He's sweeping the ground. And this motion, what he's doing this with this broom is called as sweeping, right? In cricket, we also call it as sweep shot, right? When the batsman, he almost, just like this broom, he hits a shot wherein he imitates this motion called as the sweeping motion. Okay, and with every sweep, what is happening to the broom, right? What is happening on the floor? With every sweep, the broom is covering some area of the floor. Some particular area of the floor is being covered. Okay, so this is a very simple understanding of sweeping. So coming back to Kepler's second law. So Kepler's second law is now also called as law of area. Okay, areas. So what is this law? He's saying the line that joins a planet and the sun. So center of the planet to the center of the sun. Right? So we can call it as a radius vector r. So this line sweeps out, sweeping. It sweeps out areas. Right? So it's going to sweep out equal area in equal intervals of time. So it's also called as law of equal areas, right? Law of areas or law of equal areas. Equal area in equal time. So what does this mean? Okay, see the diagram. So we have sun at any one of the focus. So say the sun is here. Okay, and we have a planet which is going in an elliptical orbit. So now suppose the planet is here at this point here. Right now the planet goes, right, let's say in the anti-clockwise direction, it goes towards this side. So let it take some time t to go from here to here. So the line joining, right, the line that joins the planet and the sun. So can I say center of the sun to the center of the planet? This is that line. So this line is sweeping out, just like the sweep shot in cricket, right? Or that person who was brooming. So it is sweeping out, jhadu mara. That R is doing jhadu. Okay, it is sweeping out this area A, this shaded area A. So let the area be A in some time t. Now, after some time, the planet will arrive here at this point. So now when I join the center of the sun to the center of the planet, I will get this line here. Now this line will sweep out another area, and you can see the two areas, their shapes, okay, they seem to be quite different. They are quite different. But if you numerically calculate the area A, if the time is the same, that's what the law is saying, equal time, equal intervals of time. So if the time is the same, then although their shapes are different, right, the areas will be equal areas in equal intervals of time. And you can see as the planet goes further away from the sun, right, here the radius vector r is quite long, okay, and again it is sweeping out some area, okay, and the area will be the same if the time is the same. So if you notice something here, right, for the planet to go, the first part, the first A and T, the planet to go from here to here, okay, the time, the arc, you see the arc length which I am showing to indicate the time needed to go from here to here is quite, big. The arc length is big, okay, here the arc length is smaller, and here the arc length is even smaller. So what about the time needed to go from here to here? Okay, so to understand that, let's see this video. Okay, it will give us more idea, because there is something hidden here which is not very clear in the statement, and that's about time and speed of the planet. Okay, so see this now. So again, we have a planet here, okay, and the sun is suppose at this focus, okay, and this is our line joining the planet and the sun. So see this, what is happening. So if you notice carefully, right, see what's happening. It's completing one circle and then it's like kind of restarting. Okay, so some area is being swept out. But if you see, especially if you focus on the speed, what is happening to the speed of the satellite? When it is closest to the sun, as it is coming closer to the sun, it is speeding up, it's faster. And as it goes away from the sun, it is slower. So why is it like this? Because the area which is being swept out, the radius vector r, when the planet is closer to the sun, right, the radius vector is small. So if that small radius has to still sweep out a bigger area, then the planet has to move faster as per the law, right? The planet will move faster when it is closer to the sun, and it will move slower when it is away from the sun. So this is also a hidden information that we are getting from Kepler's second law. Okay, and coming back to the diagram, right, if we focus on A and T, so again this here is going to be, this arc length is bigger, okay, but this time is going to be equal as this time, as equal as this time, right? So all the times are the same, although their arc lengths are different. Okay, why? The speed here will be more, slightly less here, and the least when it is farthest away from the sun. So again, as a formula, we can write that equal areas in equal time means area upon time, right? Area upon time is a constant. Okay, so this can help us in numericals. Okay. There is also another way to express Kepler's second law, and that is using a concept of angular momentum, which I'm not discussing right now. We will talk about it in the MCQs. Reason being, it's related to a chapter which is actually in 12th standard. Okay, so we will skip that part for the time being. But this formula we can note down: A by T is a constant. Okay. All right. Kepler's third law is very easy. Actually, we have almost done it. Kepler's third law of periods. Okay. The square of the time period of revolution of the planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. Okay, so quite a big statement. Let's understand slowly. Period. So when do we use this word period in physics? Okay, basically we use it for time period. Okay, so whenever there is a motion or something which happens periodically, means something which repeats itself after regular intervals of time. then the time needed for one cycle is called as time period. Okay? That's what is time period. Time needed for one cycle. Because what is repeating here? It's the motion of the planet around the sun. It's just continuing every year, right? For Earth, for example, it takes 1 year, 365 days. So every 365 days, the motion repeats itself. Okay. So square of the time period, so that t square, right, is proportional to, directly proportional to cube, okay, of this semi-major axis. What do we mean by semi-major axis? It is nothing but, if you consider the planet and the sun and the elliptical orbit, right, the line joining the center of the sun to the center of the planet, that means our R, when it is farthest away from the axis, okay, from the sun. So that is what we will call a semi-major axis, okay, of the ellipse traced out by the planet. So basically what this law means is what we already know: t square is proportional to r cube. Okay, and where did we see this? This we saw in the formula for time period, right? Even in the formula for time period, t square was proportional to r cube. But please note, the formula is the same here, t square proportional to r cube, but they are for two different things. The formula for time period was t is equal to 2 pi square root of r cube by gm, and when we had squared both the sides, we got t square proportional to r cube. But that formula was for a circular orbit. Okay, that was for a circular orbit. Now we are also, what Kepler is saying in the third law is, it is also valid for an elliptical orbit. So circular as well as elliptical orbits, both of them you can use this t square is proportional to r cube. Okay, so that is nothing but Kepler's third law. Okay, so now we will solve a few numericals. Okay, so theory is done for today. Let's begin with the numericals. So the first one, distance of a planet from the Earth is 2.5 into 10 raised to 12 kilometers, and the gravitational force between the planet and the Earth, right, is 3.82 into 10 raised to 8 Newton. So we have got two informations here. Okay, first thing we will note down. Please remember data diagram equation. Don't continue reading the question unless you have noted down what is already provided to you, right? So first thing, we can say the distance between the two planets, Earth and some other planet here. So let's say R is 2.5 into 10 raised to 12 kilometers. So please note, when we substitute the value of R, kilometer is not the SI unit for distance, it is meters. So this kilo can be added, 10 raised to 3, kilo is 1000, 10 raised to 3 can be added to 10 raised to 12. So it will become 10 raised to 15. Okay, that's fine. And the force F, we can say 3.82 into 10 raised to 8 newtons. All right, so let's read ahead. Mass of each planet is equal to that of Earth. That means, planet and Earth, these are the two planets. So it's like a planet very similar to Earth. So M1 and M2 both are same. And usually we take it as 6 into 10 raised to 24. In this question, they're giving it as 5.98. So fine, we can use 5.98 10 raised to 24 kg. And we have to find out capital G. So we already know actually what is the value of capital G. It's a constant. But still, using this information, we need to find it out. Okay. So, all right. So we know the formula. Basically, we are going to use Newton's law of gravitation. F is equal to G M1 M2 divided by R square. Or if I want G, let's gather all the other terms together. So I can keep G on one side and say this R square goes in the numerator, it becomes FR square. And then M1 M2 comes in the denominator. So FR square upon M1 M2, and what remains is G. Right? So we have all the information, we just need to substitute, right? So this is a simple substitution question. Okay. So F is 3.82 10 raised to 8. Small r here is 2.5 into 10 raised to 15. Please note that it's not 12, 10 raised to 15. We have to square the small r divided by m1 into m2, but m1 and m2 both are equal. So if I'm going to multiply, right, m1 and m2, it's nothing but 5.98 10 raised to 24 square. Okay. So now, how do we solve this further? So first of all, 2.5 square is 6.25. Please note that square of 25 is 625. So if square of 25 is 625, then 2.5 square is 6.25. Okay. Now, 10 raised to 15 square will become 10 raised to 30. 30 and 8 will become 38. 10 raised to 38. So that's the power of 10 in the numerator. Denominator, we still have 5.98 squared. And 10 raised to 24 square is nothing but 10 raised to 48. So now, I can just take this 48 in the numerator and 38 minus 48 is going to give me 10 raised to minus 10. All the other numbers remain the same. Now I already know that the power of g is actually of the order of 10 raised to minus 11. And also, before I do the log, I need to make sure that the numerator is more than the denominator. Now this denominator is approximately 6. So 6 square is 36. And here I have 6 into 3. So maybe more than 18. So around 20. Okay. So I have 20 in the numerator, 36 in the denominator. Obviously, numerator is more than the denominator. So let's adjust the power of 10. Okay, one more time. So let's make it as 10 raised to minus 11 and shift the decimal from 6.25. Let's make it as 62.5. So we have 62.5 into 10 raised to minus 11. And now definitely the numerator is more than the denominator. So we just need to solve it using the logarithm. So please pause the video here, remove your logbooks and do this calculation. Okay, and you should get this following answer. 6.676 into 10 raised to minus 11, and the units again is Newton meter square per kg square. And if you want to verify the units, check this formula. F is in Newton, R square is in meter square, mass into mass is nothing but kg square. Okay, so that is your first numerical. So please, if you have not done the log calculation, please pause here and do it first. Alright, the second numerical for today. So there are two objects which are placed 5 meters away from each other. Okay, so distance is known and they attract each other by a force of 20 newtons. So it's obviously the gravitational force. So we will note down R as 5 meters and the force as 20 newtons. Okay, then they are saying M1 is 4 times M2. So we have to find out, determine the masses of the two objects. So M1, M2 has to be found out. M1 is 4 M2. Okay, we need the values of M1 and M2 both. So how do we do it? Again, we were just going to use Newton's law of gravitation. So F is equal to G, M1, M2. Let's use small letter m. Okay, we can use smaller capital M, doesn't matter. But here, since the force is quite less, we can understand it's probably not a planet. Okay, so usually for planets we use capital M. So we can use small m. Even in the question it is small m. So G M1 M2 by R square. So let's just substitute the value of M1 because M1 is 4 times M2. So let's just put that here. So M1 becomes 4 M2. So I have G 4 M2 into M2. So M2 into M2 is going to become M2 square, right? So M2 square on one side, R square in the numerator and 4 times G in the denominator. Okay, 4 times G in the denominator, FR square by 4G, very similar to the previous question. Okay, so M2 square is FR square by 4G. So M2 is going to be root of that. So let's take square root and put the numbers. What is the value of F? F is 20 newtons. R square, R is 5. So 5 square is 25 divided by 4 times G. So if I just divide 20 by 4, I'm going to get 5. So I'm getting 25 into 5 in the numerator. So if I remove 25 from the square root, right, 25 square root of that becomes 5. 20 by 4 still remains 5. So I will get 5 root 5 divided by root G. Okay, that root G is still there in the denominator. Okay, so you can just keep it like that. And if we have already found out M2, then how do we get M1? Basically, it's just going to be 4 times that. So 4 into 5 will give me 20. So I have 20 root of 5 divided by G. Okay, so again, the values of M1 is 20 root of 5 by G and M2 is 5 times root of 5 by G. Okay, so that's the answer for question number 2. If you want, you can substitute the value of G and get it, in terms of kg. Again, it's going to be quite less, but in the answer given in the book, okay, these are the numbers. So 20 root 5 and 5 root 5 and root G has to be included there. Okay, so the next one, third numerical for today. For a planet of mass twice that of Earth and radius is 1/4 that of Earth. So two things are given to us here. Mass of the planet MP is twice that of Earth. I am converting this statement to an equation. Mass is twice of Earth, 2 times of Earth, and radius of the planet is 1/4. So RE by 4, 1 by 4 into RE, right? Or RE by 4. So RP is RE by 4, right? So find acceleration due to gravity in terms of GE. So if GE stands for Earth here, so GE is the value of acceleration due to gravity on Earth, we need to find out that same value on the planet. So we need to find out GP. Okay, so how do we solve this? So we already know what is the formula for small g on the surface of any planet. Okay, it's going to be small g is capital M by r square, right? Capital M is the mass of the planet, capital R is the radius of that planet. So if small g is gm by r square, okay, and I'm going to compare basically ge and gp, so I can understand it's a ratio question. See, here also directly a ratio has been given to us, and this also can be made into a ratio. mp by me is 2 or me by mp is 1 by 2. Okay, so it's a ratio question. So in all ratio questions, what do? We can replace the equal to sign with a proportional sign and, right, remove all those quantities which are constants here. So is capital G a constant? Yes, throughout the universe it is. Mass and radius, they are changing. You see, the planet's mass and radius are changing. So keep both of them, m by r square. So that's it. Just take a ratio, gp by ge. Now m is directly proportional, so mp by me. But r square is inversely proportional, so into re by p. So gp by ge, mp by me, but for r it's the reverse ratio, re by rp, and we have to square it. So re square by rp square. Okay, so just plug in the numbers. We already know mp by me. So if you see from here, if mp is 2 times me, mp upon me is going to be the number 2. And re by rp, so re by rp, this 4 will go in the numerator, rp will come in the denominator. So re by rp is nothing but 4, but we have to square it. So 4 square is 16, and then 16 into 2 is going to give me 32. So the acceleration due to gravity on this planet is going to be 32 times the acceleration due to gravity on Earth. So we better not go to this planet, otherwise we'll not even be able to lift our finger. Okay, because every part of your body will become 32 times, will feel 32 times heavier. Okay, your mass will remain the same, but you will feel 32 times heavier. Okay, so that's the idea here. So that's the third numerical. Fourth one, body weighs 4.5 kg weight on the surface of Earth. So what does this mean? We can say that the mass of the body is 4.5 kgs, right? The 4.5 kgs converted to weight, if you can just multiply by small g and you'll get in newtons, but in terms of kilo, it's 4.5 kgs. Okay, how much will it weigh on the surface of the planet whose mass is 1/9 the mass of Earth and radius is half? So again, very similar information to the previous question, so we can understand it's again almost a ratio question. So mp is me by 9. Mass of planet is 1/9 of Earth, so me by 9, and radius is half, so rp is re by 2. Okay, so mass is 1/9, radius is half. We need to find out the weight w, so we will have to multiply by small g, mg, right? So how do we get that? So weight is nothing but mg, so we already know the m. All I need to find out is the g, right, on the planet, gp, right, what we did in the previous question. So again the same thing, we have the same formula. Small g is nothing but gm by r square. Replace the equal to sign with proportional sign, so we are going to get capital M by r square, right? So again we will take the same ratio, right? It's the same steps repeated from the previous question. So gp by ge is going to be mp by me, right, and re by rp square. Why is the ratio reverse here? Because it's inversely proportional, right? And we have to square it. So get the numbers from the data. mp by me, mp upon me is 1 by 9, 9 in the denominator, and re by rp, so re divided by rp goes in the denominator, the number 2 in the numerator. So re by rp is nothing but 2, and 2 squared is going to be 4. So I'm going to get gp is 4 by 9 and g in the numerator, right? 4 by 9 into ge. Okay, and if I want the weight, and weight is nothing but mg, so if it's on the planet, it's m into gp, so m into 4 by 9 ge. Okay, so let's put the value of m. Okay, so the value of m here is nothing but 4.5. So can I write 4.5 as nothing but 9 by 2? Half of 9 is 4.5. So 9 by 2 into 4 by 9 into ge. So the 9 gets cancelled off. 4 divided by 2 gives me 2. So I have 2 times ge is the value of the weight on the planet. So if you want to express it in newtons, just multiply by ge, right? And ge is nothing but 9.8. So double of 9.8 is nothing but 19.6 newtons. So what does it mean here in this sum? See, in the previous sum it was 32 times GE, and now it is 2 times GE. That means the body will feel double the weight of what it is on right now on the planet Earth. Okay, 2 times GE. So if you are weighing, let's say 50 kg, if your mass is 50 kg, you will feel as if you are 100 kgs on this planet of this particular question. Okay, so 19.6 newtons if I take the value of small g as 9.8. Okay. Next one, number 5. At what height from the surface of Earth? So one thing is clear, I already know what do they want me to find out, and that's small h. Okay, the value of small g will fall to half that on the surface of Earth. So g at the height h is half of that of the surface, so g by 2. Okay, so how do we get the value of small h? So first thing here is, because we are going to deal with gh, we need to decide which formula should we use for gh. Okay, because gh has 3 formulae. So the main question here is, should I use a formula for the LEO satellites, or should I use a formula for the satellites which are at a larger height? Okay, so the answer is hidden here in this information. See what is happening to gh. Gh is becoming half of g. So if you remember the graph, from 9.8 I'm going to come down to 4.9. That means that's quite a big reduction in the value of small g. Okay, that means it's not going to happen very close to the surface of Earth. Okay, it's definitely not a LEO satellite. So we are just going to use the formula gh is equal to g into r upon r plus h the whole square. Right? Why not gm by r plus h the whole square? Because I want to find out the relationship between gh and g, right, which is coming in this formula, gh and small g. So let's use this formula. Okay, but we already know that gh is g by 2. So gh is g by 2 and gh is also this. So if I just compare these two, or if I divide these two, then I can understand this r upon r plus h the whole square is nothing but, right, the number half. Okay, r upon r plus h the whole square is half, right? This g gets cancelled off, gh gets cancelled off. Okay, and I can just understand this r upon r plus h the whole square is 1 by 2. Okay, so let's take square root. So r upon r plus h is then 1 by root 2, and let's cross multiply. So root 2 goes in the numerator, so root 2r, and r plus h again from the denominator goes in the numerator, so in the RHS, r plus h. Then let's take this r in the LHS, so I will have root 2r minus r is h, or in other words, if I take r common, h is nothing but root 2 minus 1. So what is the value of square root of 2? Square root of 2 is nothing but 1.414. Please remember this number. Minus 1 is going to give me 0.414. Substitute the value of r, which is a constant. They have not given it in the question, but you are supposed to know it is 6,400 kilometers. So very simple multiplication. If you want, you can use the logbook. Turns out to be 2650 kilometers, which is, now we can understand it's definitely not a LEO satellite. Right? LEO satellites would be somewhere around 800 kilometers, and this is like 2650, so that's quite large. Okay, so that's the 5th one. 6th numerical for today. At a certain height above the Earth's surface, the gravitational acceleration, that means small g, is 4% of its value at the surface of Earth. So what does this mean? GH is 4%. That means out of 100, it got only 4. Right? So this was your 10th standard score. You are failed. 4 out of 100. Okay, 4%. That's what it means. 4% of what? Of G, of its value on the surface. That is small g. So GH is 4 by 100 of G. 4% of G. All right. Determine the height. So we need to find out small h, and radius of Earth is a constant given to us this time, 6,400. All right. So again, which formula to use? So you can now very well understand it's only 4% of G, right? So if I take G as 9.8, or let's round it off to 10, then 10 upon 100, right? 10 upon 100 is going to be 1 by 10. So 4 by 10 is 0.4. So from 9.8, the value is going down not to half, but to 0.4. This is a very big reduction. It must be at even a larger height than the previous question. So definitely we will just go with this formula. GH is equal to G into R upon R plus H the whole square, same as the previous sum. Okay, so we know the number 4 by 100. So if I just compare equation 1 and 2, if I call them as, right? Look at these two equations and compare. You can very well understand now that r upon r plus h the whole squared is 4 by 100. So if I take square root on both the sides, okay, so r upon r plus h, right, the square goes, and square root of 4 is 2 and square root of 100 is 10. So it's very simple, 2 by 10, cross multiply again. So I have 10 from the denominator going into the numerator in LHS. So 10 times r is equal to 2 times r plus h. Open up the brackets. So 2r plus 2h. Take the 2r in the LHS. So you have 10r minus 2r is 2h. 2h is 8r. Very simple calculation here. H is 4 times the radius of Earth. So 4 times the radius is 25,600, right? That's why we could guess this already from this ratio here, 4 by 100, right? The previous sum, it was some 2,650, right? 2,500 kilometers. This is like 25,000 kilometers, okay? So it's quite a big distance because the value of G is quite small compared to the surface of Earth, okay? So moving on to the next one, the seventh one for today. Two satellites orbiting Earth, they have their critical speeds in the ratio 4 by 5. So now we are changing over to speed. So V1 by V2, let's call it as, the ratio is given to us 4 by 5. So we can clearly understand it's a ratio question. They are asking us to compare their radii of orbit. That means we need to find out R1 by R2. Compare, whenever they use this word compare in physics, means they want a ratio, R1 by R2. Okay. So what is the formula for critical velocity? Please recollect, it is root of gm by small r, okay, square root of gm by r. This is a formula for Vc. So from this, let's remove all the quantities which are constants and replace the equal to sign with a proportional sign. So can I say capital G, which is universal gravitational constant, it's a constant everywhere, and both of these satellites, two satellites, they are orbiting who? Earth. So what is this capital M here? Whose mass? It is mass of Earth. So that's anyways a constant. So G is constant, M is constant. It is this small r which is varying. So I have Vc is inversely proportional to square root of r. So if I just take the ratio from here, V1 by V2. So since it is inverse, 1 by 2 in the LHS, but 2 by 1 in the RHS, and also I have to take a square root, right? So V1 by V2 is square root of R2 by R1. So I want R1 by R2. So let's just square both the sides. So we will get 4 by 5 is a root of R2 by R1, putting the value of V1 by V2 and then square it. So 4 by 5 square is nothing but 16 by 25. 4 square 16, 5 square 25. And what we get is R2 by R1, but what is required is R1 by R2. So all we have to do is just inverse it. Take an inverse of both the LHS and the RHS. You will get R1 by R2 is nothing but 25 by 16. Very simple ratio sum. Next one, number 8. A satellite is orbiting in a circular orbit around the Earth with a speed. So circular orbit, critical speed is equal to half the magnitude of escape speed. So what do I write? Critical Vc is half of escape Ve, right? Find the height. So we need to find out small h again. So how do we solve this? We know Vc is half Ve. This has been given to us. So all we need to do is substitute the formula for Vc in the LHS and Ve in the RHS. So what is the formula for Vc? We saw in the previous question. It is root of gm by small r is equal to half into Ve. So what is the formula for Ve? It is square root of 2 times gm by not small r but capital R. Please note the value for escape velocity. Formula for escape velocity is defined from the surface of Earth. So the value is going to be in the denominator, it's capital R, right? You can recollect this formula from the previous lectures. Ve, escape, is root 2 gm by r. So if I just square both the sides, so square root gone in the LHS and square root gone in the RHS, but half square becomes 1 by 4. Okay, so I can definitely cancel off the gm on both the sides, and also 1 by 4 into 2 is going to become 1 by 2. So I have 1 upon small r, which is nothing but capital R plus h, okay, is equal to 1 by 2, because 2 by 4 become 1 by 2, and then capital R in the denominator. So now we can just again cross multiply. So 2R is equal to R plus H, or in other words, capital R is equal to H, or the height. The height is nothing but they are asking us to find out the height. Is going to be 6,400, or is that nothing but the radius of the earth? Okay. Alright, so last question for today, number 9. Calculate the critical velocity of a satellite orbiting around the earth. Okay, so we have to find out VC at a height equal to the radius of the earth. So you can understand this is nothing but the same information, the same satellite as the previous sum. Right? The height is equal to the radius, H is equal to R. Alright, so H is R. This was the answer for the previous sum, and now we have to calculate the value of VC, critical velocity. So these numbers have been given to us actually in the question, in the data itself. So we know the number 6.67, or if you want you can add a 3 there. 6.673, 10 raised to minus 11 is the value of capital G. Mass of earth, fortunately it's not 5.98, now they have rounded it off to 6 into 10 raised to 24 kg, and the radius of earth is 6,400 kilometers. I have to find out VC. So this is not a ratio, it's a very simple substitution question. So VC is root of GM by small r, and small r is nothing but capital R plus H. So, right, and the value of H is nothing but capital R. So R plus R becomes 2 times capital R. Okay. So let's just substitute the numbers. So value of G is 6.67 10 raised to minus 11. Capital M 6 into 10 raised to 24 divided by 2. Right, the number 2 is missing. So 2 times the radius of earth is 64. Kilo is nothing but 10 raised to 3, and 2 zeros will make it 10 raised to 5. In terms of meters, SI unit is meter, 64 into 10 raised to 5 meters. Okay, so we can adjust the power of 10 and divide this 6 by 2, so it becomes 3. So 6.67 into 3, and the denominator is 64. Take this 5 in the numerator, so it will become minus 5. Minus 5 and minus 11 will give me minus 16. Minus 16 and plus 24. So 24 minus 16 is nothing but 10 raised to 8. Okay. Now let's check the numerator. The numerator is 6.67 into 3. So if I just round it off to, let's say 6 3s are 18, and a little bit more than that, so maybe 20 or something like that. Okay. So the numerator is around 20, denominator is 64. Obviously the numerator is more than the denominator. So if I want to use the log, I have to adjust the power of 10. So let's make it as 10 raised to 6 and borrow 100 from it. So 6.67 becomes 667, right? 6.67 into 100 becomes 667, right? Why did I not borrow 10 and borrow 100 instead? Reason is because I still need to keep this power of 10 as a multiple of 2, because I am going to take square root. Don't forget the square root. Okay. So now it's a very simple log calculation. 667 into 3 by 64, square root of that. So when you take antilog, don't forget to take half, right, before finding out the antilog. So antilog of half log of this whole number. Okay, and 10 raised to 6, square root of that becomes 10 raised to 3. Okay, so if I'm finding out critical velocity, this 10 raised to 3 can be written as a prefix kilo. Okay, so this again, please pause the video, do the log calculation, okay, and you should get 5.592. 10 raised to 3 has become kilo meter per second for speed. Okay, so that's all for today. See you in the next lecture.